Okay, so this is a walkthrough of the distance, speed, time and Newton's laws test at foundation level. Okay, so question 1 introduces a Segway vehicle that can be used as a method of transport for a person. The person leans forward to make the Segway accelerate and leans backwards to slow it down. Okay, so which is deceleration. It is recommended that short training sessions are carried out before using the Segway on a busy pavement. We've also got a picture here where the Segway is upright, so we can assume that it's travelling at constant velocity. Okay, so we've got a velocity time graph here, and this relates to a short Segway training session that's carried out on a dry pavement. The person riding the Segway is instructed to carry out an emergency stop during the training. So at time 0, the Segway is moving at 0 meters per second, and then over the period of 3 seconds it accelerates to 6 meters a second. It then travels at a constant velocity of 6 meters per second until 9 seconds. So that's a total time there of 6 seconds. At this point, or somewhere around here, they're told to stop. They stop the Segway and it comes to a halt after 11 seconds. So the questions ask, using the information on the graph, answer the following questions. So between which point, A to B, B to C, or C to D, is the person leaning forward on the Segway? So it's actually asking you at what point is the person accelerating. And of course, they're accelerating between A and B. So at this point of the graph here to here, so the correct answer is A to B. The next question moves on, and you're given an equation actually in the question, which is quite common, and you're asked to calculate the acceleration during the first 3 seconds and state its units. So in order to do this, we need to know the change in velocity, and we need to know the time over which that takes place. Now you're given the time here, okay, so we could put that into the equation, preparation for finding the change in velocity. To find the change in velocity, we need to look at the graph, and we notice that the velocity is 0 to start, and then after those 3 seconds, the velocity is 6 meters per second. So the change in velocity is 6, take away 0, which of course is 6 meters per second. So if we replace that, it's easy. Equation. We get 6 meters per second. Okay, and so there was a mark for the equation. Of course, 6 divided by 3, that would give us 2. But what many people failed to get correct was the units, because 6 meters per second divided by seconds actually becomes 2 meters per second squared, okay, or 2 meters per second. Those are the units of acceleration. Many people put meters per second, which of course is the units of velocity. Okay. The next question generally was well answered. You were asked now to calculate the resultant force. Okay, so resultant force is calculated using the equation that once again is given to you in the question, which is quite handy. You don't need to start looking at the front of the paper. And so the force is the mass of the rider and Segway, which is given to us here. Okay, so it's in the question there. So that would be 110 kilograms, and that's multiplied by the acceleration, which you've just calculated up here. So that's 2 meters per second. Of course, 2 times 110 is 220 newtons. We don't need to worry too much about the units because they're given to us in the answer. But kilograms, meters per second are the same as newtons. Okay, if we move on to the next question, open the page. So in our next question, it introduces the idea of reaction time. So the reaction time of the person riding on the Segway is 0.6 seconds. Use the graph on page 8 to determine the time during the training session at which the rider is asked to carry out the emergency stop. Okay, so what this is telling us is it takes 0.6 seconds between being told to stop and the Segway actually starting to stop. So if we have a look back at the graph on page 8, we can see that the Segway starts to stop here at point C, and if we can trace down the graph, point C is at 9 seconds. So 0.6 seconds prior to that, okay, the Segway driver was asked to stop, so it would be 9, take away the 0.6. So if we go back to the question, okay, we've got 9 seconds where we can see the Segway driver starting to stop. However, he was actually asked to do so, or she was asked to do so, 0.6 seconds prior to that, but it takes that long to respond. So the actual time was 8.4 seconds. Okay, so 8.4 seconds was when they were asked to stop. It took them 0.6 to actually respond. Okay, Newton's first law of motion states an object will remain at rest or move at constant velocity if the forces acting on it are balanced. A student states that during the Segway training session, balanced forces act on it for 11 seconds. Explain whether you agree with the student. Okay, so if we have a look back at the graph again, we can see that the Segway driver does actually travel for 11 seconds. However, the only point at which there are balance forces acting on this rider are between points B and C, because the Segway neither accelerates nor decelerates. So at this point, it is under balanced forces. So the statement is incorrect, and that happens between 3 and 9 seconds. Okay, so you would disagree as constant velocity only occurs between 3 to 9 seconds. Okay, so constant velocity is what happens when the object is under balanced forces. Okay, next question. The graphs below show and opposite show 3 possible training sessions carried out by the same Segway rider. Lucy says graph C would represent the emergency stop carried out on an icy pavement. Explain whether you agree with Lucy. Okay, so if we quickly have a look at these graphs, this one shows a similar acceleration, okay, but a much quicker deceleration, okay, which is, so the Segway is coming to a halt after only 1 second here, which is unlikely on an icy pavement. An icy pavement, the Segway may start to slide, and it would take longer to come to a halt. On this graph at the top here, we can see that the time that they start to stop is again 9 seconds. In fact, this looks remarkably similar to our original graph. Okay, so again, this is unlikely to be an icy pavement because in the original text of the question, it was stated that the pavement was dry, on which the okay, having some technical difficulties here. So let's see whether we can sort those out. Okay, we'll try and carry on. So this final graph here, we can see that the stopping time starts at 9 seconds but goes on for till 13 seconds, which would suggest it takes a lot longer to stop, and that would be possible or consistent with a icy pavement. Okay, so the question, we can agree with Lucy because the total stopping time is longer due to skidding on icy surface. Okay, so we need to make the statement to agree or disagree for 1 mark, and then we need to explain our reasoning for the 2nd mark. Okay, so moving on to our next question. Again, this deals with stopping distances. So the overall stopping distance of a car is made up of 2 parts. The distance that the car travels when the driver is reacting is the thinking distance, and the distance that the car travels after the brakes have been applied is the braking distance. So we've got a diagram to explain that. It is important to notice this section here where it tells us that the overall stopping distance is the sum of these 2 distances. Okay, so we've got a graph here that shows us the braking distance and the thinking distance as 2 separate lines as the speed of the car increases. Okay, now these speeds are in miles per hour, which is the speed that we normally quote car speeds in for whatever reason. It is important to note this table at the bottom, which is a conversion table for miles per hour to meters per second, because meters per second are the metric units that we would normally use in physics calculations. So we might need this later. Okay, so we can see that the thinking distance is a straight line. Okay, because the thinking time that you take over things is pretty constant, but as your car travels faster and faster, then that thinking distance gets greater. The braking distance is a very steep rise, an exponential rise almost, as the car gets faster and faster. So, first question says, it is suggested that both thinking distance and braking distance are directly proportional to speed. Explain whether this suggestion is true. So it is untrue because the braking distance increases more and more as speed increases. And we could suggest there's an exponential rise there. Okay, so we just have a quick look at the graph. This curve is getting steeper and steeper and steeper. Okay, as the speed of the vehicle increases. Okay, the next question. Again, a question with an equation provided for us, which is always nice. So it says here, use the information on page 16 and the equation to calculate the thinking time of the driver when traveling at 40 miles an hour. Okay, so what we need to take from the graph is the distance and the speed, okay, at 40 miles an hour. Okay, so we need to remember that that's in 40 miles an hour. So at this point, we need to refer to our table. Okay, so our table tells us that 40 miles an hour is the same as 18 meters per second, and that's a speed. Okay, so if we put into our equation, we want to know the thinking time. So that's distance divided by speed. So we've just established that the speed is 18 meters per second. Okay, a lot of people put 40 straight in there, they didn't convert it. Oh, you can't see that. So that's 18 meters per second because that's what 40 miles per hour is in meters per second. And then we need to find the distance, okay, and this is for the thinking time. So at 40 miles an hour, which is here, if we go up to the thinking time graph, then we can see that that's 10 meters and a tiny square, that's 12 meters. So 12 over 18, okay, if you put that into your calculator, you'll discover that it's 0.6 recurring, okay, so it's 0.6 recurring seconds. Okay, the next question, it says use the information on the graph to complete the table below, and so it wants us to calculate the overall stopping distance. So if we go back to the previous page, we notice that overall stopping distance is the total of the two other distances, the thinking and the braking. So what we need to do is read the graph carefully and work out what the overall braking distance is, sorry, stopping distance is using these two values. Okay, so the table wants us to do it from 20 up to 70, okay, or including 0. So at 0, obviously 0 and 0 is 0, okay. At 20 miles per hour, the thinking distance is 6 meters, and this braking distance is also 6 meters, so that's going to be 12. 30 miles per hour, then we've got 9, and we've got 14, 9 and 14, which of course is 23, okay, or thereabouts. I was reasonably lenient with these distances. Then we've got 12 and 24, which is 36 in total. Then we've got 15 and we've got 38. So 15 and 38 is 48, 53. Okay, and then 60, we've got 18. Okay, 18 and 35. Okay, which is 48, 53. No, it's not. Resort to a calculator, doing things under pressure. $72. Okay, so we've got 72, and finally we've got 95. Okay, so if you transfer these figures into your table, next page. Okay, so 0, 12, 22, 36, 72, and 95. And I gave you a plus or minus 2 there, okay, for in order to be a bit fair. Then we need to plot these points on the grid to draw a line to show how the overall stopping distance depends on speed. Okay, so at 0, obviously we had a 0. At 20, we had 12, which would be there. At 30, we had 22, which would be there. At 40, we had 36, which would be there. And then we had 53, which would be there. That doesn't help. And then we've got 72, which would be there. And 95, which would be there. Okay, and then it says draw a line to show how the overall stopping distance. So this line, like the braking distance line, is a curve. Okay, so I would be tempted to turn my page around and then just sort of practice it once and then go like that, a nice freehand curve. Okay. And the 3 marks were for accurate plotting and drawing a nice smooth curve. So if your plotting was inaccurate or you had some miscalculations that give you a wrong plot, then you may have lost a mark. If your line was a very straight line and didn't show any curve, you may also have lost a mark. Okay, moving on now to the final question. Okay, again, a question that we're given an equation. Okay, so use the equation mean speed equals distance travelled divided by time. No, I've missed a whole page here, so I'll do it foolish. Just bear with me. Here we go. Let's go again. So explain how the start again. The speed limit along a road outside a school in Cardiff was 30 miles an hour. Okay, the council decided to reduce this to 20 miles an hour in 2017. The entrance of the school is situated 15 metres after a bend in the road. Explain how the change in speed limit affects the chance of children getting knocked down as they cross the road outside the school entrance. Use data to support your answer. Okay, so how does it affect the chances of getting knocked down? Basically, it reduces the chances. I think most people were able to see that. But what a lot of people lacked was using the data to back that up. So reduces the chances of getting knocked down. Okay, now from the diagram we can see this distance here has been placed there because it's approximately the distance that as the vehicle comes around the corner, they'll be able to see pupils in the road for the first time, and they'll need to stop. Okay, and they've got 15 meters to stop. So if we have a look at our graph, okay, and find the total stopping distance at 30 miles an hour. So this is the original speed limit. So at 30 miles an hour, they see the child and they will stop in 22 meters. Okay, which obviously is 7 meters further than they could do with stopping because the children at 15 meters. Whereas at 20 miles an hour, going to stop at around about 12 meters. Okay, so obviously at 20 miles an hour, they will stop short of the pupils, whereas at 30 miles an hour, sadly, they will run over the pupils, okay, by 7 meters. So you could say at 30 miles an hour, the stopping distance is 22 meters. At 20 miles an hour, it is 12 meters. No collisions at this speed. Okay, so that reduction in 10 miles an hour makes the school a great deal safer. Okay, right, now we've got the final question. So this is quite a common experiment, okay, but it was quite well explained, and the results table rather, reasonably self-evident. So we've got a ramp here that is higher, can be made higher and higher, and we want to time how long it takes for the car to travel from here 2.5 meters along the track. Okay, so basically this part of the experiment is simply to accelerate the vehicle, and then from there 2.5 meters is to see how fast it's going. So they investigate how changing the height of the one end of the track affects the time taken for the car to travel 2.5 meters off the track. One student releases the car, the other uses a stopwatch to measure the time. They do this 3 times for each height. The results are shown below in the table. Okay, so identify the controlled variable in the table. Well, I think every one of you managed to identify that this is the controlled variable because it's the same, so that distance travelled. And then if we move on to the actual final page. So again, we're given an equation, and to be fair, most people will be able to use this without any issues at all. So the mean speed is the distance travelled divided by the mean time. To calculate the mean speed of the toy car when the slope is set at a height of 10 centimeters. Okay, so we look back at our table, and you can see that at 10 centimeters, the mean time has been calculated for us as 4 seconds. If you did the calculation, you actually find it's 4.03, but it's 4 seconds to a 1 decimal place. And we know the distance travelled is 2.5 meters every single time. Okay, so if we turn to the final page, so we need to know the distance travelled was 2.5 meters, and the mean time is 4 seconds. Okay, and that gives us an answer of 0.625 meters per second. So 0.625 meters per second. Okay, so move on to the next one. Describe how the mean time changes as the height increases by 10 centimeter steps. Now, there are 2 marks for this, okay? So the first observation is that it decreases, so it increases, no, start again. The time decreases, okay, because the car gets faster. So it decreases. Okay, however, if we look at how it decreases, the steps in the height are 10 centimeters, 10 centimeters, 10 centimeters, 10 centimeters. But if we look at how the time decreases, okay, it goes from 4 to 3.1, so that's a drop of 0.9 of a second. Okay, then it drops down by 2.5 to 2.5, which is 0.6 of a second, and then it's 0.4 of a second, and then it's 0.2 of a second. So the steps between these decreases gets progressively less and less. Okay, so it decreases by smaller increments for every 10 centimeter increase in height. So the reason there's 2 marks for that is you've got to recognize that that's happening. And then the second part is for only 1 mark. So describe how the mean speed changes as the height increases. Okay, and so some people went through and calculated the speed, but we can probably say that the speed increases as it's for 1 mark. Okay, so as the height gets higher, then the car travels faster, and therefore the speed increases. Okay. Now in part C, one student says the most repeatable data is for the height of 50 centimeters. Explain why this statement is incorrect and write a similar correct statement. Okay, so if we have a look at that data, 50 centimeters. Okay, then we can see that we've got 2 second time, 1.8 and 1.9. So the difference between the highest and the lowest is 0.2 a second, which might not seem a lot, but it is actually a 10% range. Okay, so it's a big range for those numbers. What we're looking for here is the most consistent set of results. Okay, so if we have a look up here, we can see that for 10 centimeters, we've got only a 0.1 range, and 2 of the results are exactly the same. So that is actually quite a high quality data set. And I think that is actually the highest quality data set with the least variance in timings. Okay, so we could say that so these results have a large range. Okay, so the range between the results is quite large. And then if we rewrite this sentence, we could say the most repeatable data is for a height of 10 centimeters. Okay, because that data is far closer together. And then finally explain why using a timer connected to light gates positioned at the start and end of the 2.5 meter track will improve the results. Okay, so they will be more accurate and precise. And some people quite rightly said they remove human error. Okay, because the light gates are connected to a computer which automatically record the start and end time and therefore can work out the time of the journey. Okay, sorry about the interruptions in the middle. My camera's now standing up on its own. Thank you very much.